Favourite fact about the universe? This is an easy one, I think. It's the size of the universe. The bit we can see, which is what's called the observable universe, has about between 1 and 2 trillion galaxies in it, depending on how little tiny galaxies and big galaxies, but it's let's say 1 trillion-ish, something like that. And that is only a small part of the universe that exists, so we're sure of that. Whether the universe is infinite in all directions, we don't actually know, but as far as we can tell, it could be. So my favourite fact about the universe is that it might be infinitely big. They're formed at the end of stars' lives, or at least the smaller ones are. So what happens when a star is burning its fuel, like the sun is now? What's happening is that the sun is carrying out nuclear reactions in the core. They're called nuclear fusion reactions. That releases energy and that keeps the star up. But the star is burning a lot of fuel. The sun is burning, let me remember the number, it's 500 or 600 million tons of fuel every second. Hydrogen fuel can burn it into helium. So that can't go on forever. In the sun's case, it'll last for about another 4 or 5 billion years. When it runs out of fuel, then gravity will take over and the star will start to collapse. And if the star's big enough, there's no known force, even the rigidity of matter, that will stop it collapsing. So it collapses and collapses and collapses and forms a black hole. And that's how the so-called stellar mass black holes are formed.
Why isn't Pluto let's say conservatively 200 billion, that's 200,000 million stars in our galaxy. And the current estimate for the number of galaxies in the observable universe, which is the bit we can see, is around 2 trillion.
There's no reason to distinguish Pluto from a load of other
million.
And so you have to say,
that's
well,
right, 2 million. So we have something like, let's say, 2 million galaxies that we can see in principle. And each one of those has 200,000 million stars, let's say, on average. So you have to multiply 2 million by 2,000 million. So that's a 6 and a 6 and a 6, that's 18, 19, 20, 21. So it's something like, let's say, 4 with 21 knots after it.
Just because
but let's say, conservatively, 200 billion, that's 200,000 million stars in our galaxy. And the current estimate for the number of galaxies in the observable universe, which is the bit we can see, is around 2 trillion. So that's 2 million.
The ingredients in our bodies were assembled in the hearts of long dead stars over billions of years, and have assembled themselves spontaneously into temporary structures that can think and feel and explore, and then those structures will decay away again at some point, and in the very far future there'll be no structures left. So there we are, we exist in this little window when we can observe this magnificent universe. Does the Big Bang disprove the existence of God? No, I mean, I don't know why. It's kind of the opposite actually, isn't it, in some sense, because very quickly, historically, Georges Lemaitre, who's often described as the father of the Big Bang, was a priest as well as a mathematician, and he was delighted that Einstein's theory certainly appears to suggest that there could have been a beginning. Einstein didn't like that, he wanted the universe to be eternal, but Einstein's theory strongly suggestive of a beginning or an end. And Lemaitre, as a priest, was happier with that, because if you think about what a beginning is, you could call it in that language a moment of creation. So actually, historically, Lemaitre was more predisposed to accept that the universe might have a beginning, because he saw that as a more of a suggestion that there could be a God, because then you have a thing as a creation. They're formed at the end of stars' lives, or at least the smaller ones are. So what happens when a star is burning its fuel, like the sun is now? What's happening is that the sun is carrying out nuclear reactions in the core. They're called nuclear fusion reactions. That releases energy and that keeps the star up. But the star is burning a lot of fuel. The sun is burning, let me remember the number, it's 500 or 600 million tons of fuel every second. Hydrogen fuel can burn it into helium. So that can't go on forever. In the sun's case, it'll last for about another 4 or 5 billion years. When it runs out of fuel, then gravity will take over and the star will start to collapse. And if the star's big enough, there's no known force, even the rigidity of matter, that will stop it collapsing. So it collapses and collapses and collapses and forms a black hole. And that's how the so-called stellar mass black holes are formed. What we do know about Earth is that although life began, let's say, 3.8 billion years ago, it wasn't until around 600 million years ago or so, that, or maybe at most 700, that you see any complex multicellular organisms at all. The one thing that is true is that we seem to be, all complex creatures seem to be, we're called eukaryotes, right, which is cells with a cell nucleus and all that kind of stuff. And they look like they're the merger between two simpler life forms, bacteria and a thing called an archaea. An archaean. So it looks like somewhere in 2 billion years ago, whatever it was, in some ocean, the bacterium cell got inside the archaean and survived as a symbiotic organism, essentially, and then somehow, unbelievably, managed to reproduce and replicate in that configuration. And that does seem to be the origin of all complex multicellular life on Earth.
So very early on in the life of the solar system, so let's say 4.5 billion years ago or so, we think that a planet about the size of Mars collided with the young Earth. And it's a glancing blow, actually, which caused a lot of rubble to go out into space, formed momentarily a ring around the Earth, somewhat like the rings around Saturn, but then that ring very quickly coalesced into the Moon. So we think that the Moon is made of mainly bits of the Earth and also bits of this other planet that glanced off it about, I'm not sure of the exact date, I think it's something like 4.5 billion years ago. It's very, very early, very soon after the Earth formed.
What's going to wipe out humans first? If I was to guess, I would say humans, and that's not supposed to be a joke. I think that the biggest threat to our civilization is us. So we have complete control over that, but it might not help us, which says something about our stupidity. What is space? It's also a thing that, you know, it's the distance between stuff that you throw about, but whatever. Right. What is the best bit of evidence for alien life? We don't have any evidence for alien life, is the answer.
We've seen no evidence of any civilizations out there beyond Earth, and that's a surprise. There's a reasonably plausible explanation for that, which is biology, which is that if you look at the history of life on Earth, then you see that life began pretty much as soon as it could here on Earth. We have evidence there was life 3.8 billion years ago, something like that. And the Earth's 4.5 billion years old, so pretty quick in geological time you get life. But then if you talk about advanced life, complex life, multicellular life, then there's no evidence at all back beyond a billion years. Actually, really, in the fossil record, 650 million years ago or something, you start seeing the first evidence of complex creatures. So that means that on this planet, it took over 3 billion years to go from a single cell life to anything more complex than a single cell. And then another 500 million years or so to go from the multicellular things to a civilization. So it's 3.5 to 4 billion years. It's a third of the age of the universe. That is a really long time.
So in the solar system, we know there's only one place, Earth, which has complex life, and certainly a civilization like ours. It could well be that there are microbes below the surface on Mars today, or there may have been microbes on Mars in the past when Mars had rivers and lakes and quite possibly oceans for a few 100 million years. So there could have been Martians, but they would have been little microbes, bacteria-like things at best, I think. And on the moons of Jupiter and Saturn, like Europa, there are oceans below the surface, and we think the conditions are right for life to have started, but we don't know because we haven't been there. So if there are aliens in our solar system, there'll be little single-celled things waiting for us to find them.
You need to know that there are 2 trillion galaxies in the observable universe. You need to know that the Milky Way galaxy has got 200 billion stars. Most of those stars now we know have planetary systems. We estimate there are something like 20 billion Earth-like planets, or potentially Earth-like planets, in the Milky Way galaxy alone. So if you're asking questions about what is my place in the universe, you need to know those things.
What are the northern lights? So it's the solar wind, which is particles that are ejected from the sun, stretching the Earth's magnetic field, and then the Earth's magnetic field reconfigures and snaps back on the night side of the sun, and those charged particles are accelerated down towards the poles, and they excite molecules in the atmosphere, which means that they cause them to emit radiation, photons, and so the oxygen, the nitrogen, and so on, and you get different colours.
And we can actually look so far out that we can see almost back to 13.8 billion years ago, which is very close to the Big Bang. So we can look to light that began its journey before there were galaxies. And that's the oldest light in the universe, which is, by the way, one of the pieces of evidence when people say, I don't believe in the Big Bang. The answer is, well, you can see it. So, it's just there. You can see it. We have pictures of it. That light, it turns out that there are sort of structures or ripples in that light, which we can use as a ruler. So quite literally, as a ruler on the sky. And then because that light's been travelling through the universe, we can see how that ruler has been distorted as the light has travelled through space. And so we can infer whether space is flat or curved, or how it's warps, if you like, just from that measurement. We can look at the most distant light we can see, which is something called the cosmic microwave background radiation, which is, if you imagine looking out, if you look at the Andromeda galaxy, which we can see with the naked eye here in LA, you can see it's the most distant object you can see with the naked eye, and it's about 2 million light years away or so, which means the light took 2 million years to get to us. So it's a long way away, but it's very big. So as you look further out into the universe to more and more distant galaxies, you're looking further back in time, because you look at something that's 1 billion light years away, then the light took 1 billion years to get to us. So you see it as it was 1 billion years in the past. So at the Large Hadron Collider at CERN in Geneva, it's 27 kilometres in circumference, and we accelerate protons around that ring to 99.999999% the speed of light, very close to the speed of light. And at that speed, time passes 7,000 times more slowly for the protons than it does for the experimenters on the ground. So that's a 7,000 times time shift into the future, if you like, if you go that close to the speed of light.
The way we understand physics at present, photons travel at the speed of light, not because they're light, but because they have no mass. So it should really be called the speed of massless particles. And that's built into Einstein's theory. It was subsequently realised, basically. So will we ever travel at the speed of light? No, unless you have no mass, in which case you have to.
So the moon is an important component of the Earth's, of stabilising the Earth. So the Earth, as you know, spins on its axis. It's like a little spinning top, and it's tilted at 23 degrees, which gives us our seasons. That's why we have seasons. But that spin is not completely stable. It does wobble, and that's called the precession of the equinoxes. So it wobbles around like a gyroscope. But the stability of that appears to be linked very strongly, or is, I think I should say, is dependent on the moon and the moon's orbit. We have a very big moon. It's unusually large compared to the planet, and that stabilizes the Earth's spin axis and stabilizes our seasons. So the current, the origin itself, we don't even know whether it had an origin. We don't know what the beginning of time actually means, because we don't know what time is. We're beginning to suspect, from the study of black holes in particular, that it emerges from quantum entanglement, but I won't talk about that. I haven't got much time. So the point is, we don't know what it means, the origin, whether it had an origin in time or not. In terms of the Big Bang, we very strongly suspect that was an event in a pre-existing universe. So we think that space and time existed before that, and the universe was probably cold and expanding very fast, and that expansion slowed down, and the slowing down of the expansion is what we call the Big Bang. That's called inflation. How will the universe end? Well, the current best guess, or best estimate, is that it will carry on expanding forever, that the universe is accelerating in its expansion, which is a great mystery, because before that discovery, we thought, well, gravity is always attractive, and so it should be, we've got all these galaxies in the universe, and the universe has been expanding since the Big Bang, and so it should at least be slowing down. And there was even a question as, is there enough matter in it to slow it down so much that it stops and recollapses again? But this new discovery, it's only a decade old or so, that the universe is accelerating in its expansion, suggests that it will continue to accelerate unless some new physics appears that we don't understand, and so it will just continue to expand forever. So we think that we're in a universe that will continue to expand, essentially doubling in size on a fixed time scale, which is about 20 billion years. So we think every 20 billion years into the future, forever, unless something happens, the universe will continue to expand and double in size.
We're at the threshold now of spreading out from the Earth, becoming a multiplanetary and ultimately an interstellar civilization. So we know how to do it. So we're at the threshold of a remarkable transformation in our fortunes. But I'm worried that just because of our internal differences as people and countries living on this one spacecraft essentially, then we won't manage to get to that. It's within our grasp. So a magnificent future is within our grasp. And it worries me that we might not be able to grasp it.